Okay, hello everyone. Welcome to the exercise class 3 of EM1. I'm Alan. So today I've prepared two questions about the boundary conditions in electromagnetism, focusing on the electric potential and also the magnetic vector potential. So please take a look and try to do the questions before continuing the video. So if you haven't finished the questions, pause the video now. Okay, counting through from 3, 2, 1. Okay, I guess everyone have tried the question now, and let's start talking about the questions. So for the first question, we have a disk. Okay, let me draw a disk first. We have a disk here, and we like to find with surface charge density sigma and radius r, and we would like to find the electric potential at the center with a distance z. Okay, first of all, let me write down the general equation for electric potential. Phi is equals to 1/4 pi epsilon naught integrating sigma over r for the whole area. The r here is the distance between the observer and the source position. Okay, so I think of you should be familiar with these kind of questions. So for these kind of questions, first of all, we can divide the disk into a bunch of range, which is indicated by the color red here. So let's say the ring has a radius of small r. Okay, so let me draw the top view of the ring here. Oops. Okay, perfect circle. Okay. So now, if we divide the disk into a different small ring with radius small r, and then the width of the ring is that dr. The area of the ring is equal to the circumference of the ring multiplied by dr. We can treat this ring as we can cut it at one point and then treat it as a rectangle. So it's like a rectangle with the length 2 pi r and the width dr. So for this ring, since the surface charge density is sigma, which is uniform, so we have the charge at this ring equals to sigma multiplied by the area, which is 2 pi r dr multiplied by sigma. So right now we can find the electric potential. We just have to integrate the contribution of all the ring. So for each ring, the distance between the ring and the observer is just square root of r squared plus c squared. Okay. And right now we just have to plug in everything into the equations. we have the charge of the ring over by the distance. And then we just integrate this contribution from 0 to big R, which is the radius of the disk. Okay, so right now I just have to finish this integration. Okay. So after moving all the constant out of the integral, we just left with r dr over square root of r squared plus c squared, and then integrated from 0 to big R. And this is not difficult to calculate. We just have to use the method of substitution. So RDR, we can replace it by 1/2 of d r squared plus c squared. Okay, so and then therefore we can perform this integral very easily. The result is square root of r squared plus c squared with lower bound 0 and upper bound r. And after plugging in all the constant, we can find out that the potential is equals to the constant sigma over 2 epsilon naught at front multiplied by square root of big R squared plus c squared minus. And here's the part is a little bit tricky, because when we substitute 0 into the R, we get square root of c squared. And this guy here is actually square root of c. Okay, square root of c. Sorry. It should be this absolute value of c. Because we didn't indicate whether, we didn't specify whether the observer is on top of the disk or below the disk. If the observer is below the disk, then Z should be a negative value. So when we square it and then take the square root, we should take the absolute sign. So now we have our solution here. Minus absolute of Z. Okay, so let me divide it into two cases. For Z greater than 0, we have phi equals to sigma over 2 epsilon naught multiplied by square root of r squared plus z squared minus z. And for z smaller than 0, for negative z, we have similar thing here, but plus z. Okay. But when we substitute z equals to 0 for both cases, we obtain the same values. So therefore, it is quite easy to show that the first boundary condition is satisfied. The electric potential above and below is continuous, which means that the difference between the electric potential at the boundary is equal to 0. Okay, but that is not the case when we take the derivative. So when we take the derivative here, so for the second boundary condition, so for this one is the first boundary condition. And for the second boundary condition, we have to take the Laplacian of the electric potential. Okay, so for Z, for positive Z, we have the Laplacian of phi. Basically, we just have to take the partial derivative with respect to Z, because the potential is only depends on Z and is independent of X and Y. Okay, so when you perform the derivative, we can get this solution. And for negative Z, we perform the same derivative, but this time we have +1 here because of the plus Z in the potential. Okay, so when we substitute Z equals to 0 for both cases, then the difference is not equals to 0. So for nabla phi about minus nabla phi below, we can get minus. The first part is cancelled out, so we just have the second part here. The first part is cancelled out, so we just left with the second part here. So okay. So now we have shown the second boundary condition is also satisfied. So as we have taught in the lecture, the divergence of the electric potential is basically minus of the electric field. So this shows that for the electric field, it is not continuous if across the surface, if we have some charge, non-zero charge density on that surface. Okay, so that is question 1. Okay, for questions 2, we have two infinitely large sheet with surface charge density plus and minus sigma moving. Okay, let me define the coordinates here. X, Y, okay, and Z. So these two planes are distant, have a distant d, so the Z coordinate are plus d/2 and minus d/2 respectively. So let's say these two plates is moving in y direction with velocity v. Okay, so for the first plate, it has the surface current density K equal to the surface charge density multiplied by the velocity. Okay, and for the second plate, we have the same magnitude, but with a sign difference because it's having a negative charge density. Okay, so to calculate the vector potential, let me first write down the general equation here. mu0 over 4 pi multiplied by this current, surface current density over R. Again, the R here is the distance between the source position and the observer, and integrated over the area. Okay. And this time, since we have two planes, we have to divide this integration into two parts. Okay. For the upper part, okay, let's say let's say the observer is located at Z. Okay, because of symmetry, it doesn't matter the X or Y coordinate of the observer. We can always move the observer on the Z axis. Okay, so let's say the observer is located at a distance Z above the center. So for the first plate, okay, let me move this part over here. Okay, so for the first plate, we have to integrate the source. So here I draw a small, okay, maybe I use another color. Here I draw a small unit area in color red here. So for this small unit area here, it has a current, surface current density K1 here, as divided below, and its source position in the coordinate. Okay, let's say the coordinate is R and theta here. The theta is just the polar coordinate theta. Okay, so the distance between the source position and the observer is just R squared plus Z minus D over 2 square, because the plate is located D over 2 above the center. Okay, so for the first part, okay, so since we are using polar coordinate, the unit area D8 here is just R dr d theta. Okay. Over the distance. Okay, so for the boundary of this integral, since this is an infinitely large plane, so R goes from 0 to infinity, and theta goes from 0 to 2 pi. Okay, and the same for the lower plate, and this time I'm using R prime and theta prime, and another set of parameter to avoid confusion. So again, we have the surface current density. This time is minus sigma V, because it contains the surface charge density minus sigma. And for the source, for the distance between the source position and the observer, okay, let me draw it here. Maybe this time draw on the left. So this is R prime, and this distance using Pythagoras theorem, which is R squared plus Z plus D over 2 squared. Okay, R prime here. So since these two integration does not depend on theta and theta prime, you can just directly integrate it over from 0 to 2 pi. So we can factor out the 2 pi, and then for the remaining part, and also the constant, sigma and V. And then for the remaining part, we have, again, this integration. Okay. So since these two integrations have the same upper bound and lower bound, we can write it as, we can group this integral together. Let me, this is running out of space. Okay, let me add the right hand here. And then the integral here. Okay. Okay, and this form of integral looks very familiar because we have performed exactly the same form of integration in the last questions. So we can just basically copy the answer from the previous questions. So, okay, let me just write down the answer here. Okay, from 0 to infinity. Okay, but in these questions, when we up to this step, you may feel a little bit weird, a little bit strange, because when you substitute r equal to infinity into these expressions, we obtain infinity minus infinity. Okay, especially if you try to calculate the vector potential for one plane only. If you do the calculation one by one, and if you try to calculate the vector potential of one plane only, you will obtain the vector potential to be infinity, because when you substitute R equal to infinity into the expressions, you just get infinity in the vector potential. And that's it's actually very normal, because we are using, okay, let me highlight it, because we are using these general equations here. What does it mean? Is that if we use these equations here, we basically assume that the vector potential at the infinity is equal to 0. Because as you all have learned, for no matter electric potential or vector potential, we have to set a certain reference point to calculate its values. So the most common reference point we used in all the calculation is to set the potential at R equals to infinity to be 0. So for R tends to infinity, the potential or the vector potential drop down to 0. But that is not the case for infinite plane uniform surface current density, because for one plane only, if you calculate the magnetic field, you will find that the magnetic field above the planes and below the planes are all constant, which is similar for the electric case. If you have an infinitely large planes with charge density sigma, then the electric field above and below will be constant. Then when you try to calculate the potential, no matter the electric potential or the vector potential, you have to integrate it from infinity to the observer distance set. So since the electric field or the magnetic field is constant throughout all space, you basically the resultant potential equals to the constant multiplied by infinity, because the distance between the observer set and the reference point you chose, infinity, is infinity. But in this case, since we have two opposite current charge density, if you calculate the B field separately and sum it all together, you'll find that the magnetic field above the two planes and below the two planes are 0. So for this case, we can still set the vector potential at infinity to be 0. Okay, which means that for this expression, we just have to take the limit R tends to infinity when we substitute it. So how to do it? Just a little bit tricky. We just have to something like rationalization. Okay. Now taking the limit, so let me move it here. Maybe move it down here, because I may run out of space here. Limit R tends to infinity multiplied by the same two items, but this time adding these two together over the same. Okay. And then if we substitute R equal to 0, we get, again, absolute Z minus d over 2 plus absolute values of Z plus d over 2. Okay. So to evaluate this limit, after I'm multiplying this thing, which is basically 1, I'm doing nothing. But after we multiply this term, we can get this in the denominator plus and this as the denominator. And we can find that the r squared term here cancel out. So therefore, when we take the limit, there's no r term in the numerator, and we have r term in the denominator, so the whole terms essentially goes to 0. Okay, so what we left are the terms when we substitute r equals to 0 in doing the integration. So this is the final result. Okay, so let me divide it into 3 regions. Okay, the first region set above the 2 planes, set greater than d over 2. We have the potential equals to a constant. And same for set equal to d over 2 below the 2 planes with just a minus sign change. And for the potential between the planes, we have the vector potential equals to, oh, I missed the y here in both cases. Okay, let me move down the third case a little bit. Okay, for set in between the 2 planes, we have the first term being for the first term inside the absolute side being negative. So after we take the absolute value, we have to add an extra negative sign. And for the second term of the absolute value, you can just keep it. Okay. Okay. Swap the 2 terms. Okay. Sorry. So for the first term, sorry, it should be positive because Z is always greater than minus d over 2. So for the first term, inside the absolute values, inside the absolute signs is always positive. So this term remains the same. But for the last term, we have to change the sign because the term inside the absolute sign is always negative. So the d over 2 cancel out, and now we have sigma naught. We have mu naught sigma v z. Okay. So for the first boundary conditions, we now have two surfaces here. Okay, so for the upper plane, we have the vector potential above is a constant, so we just copy it. But for below, we can substitute z equals to d over 2. Okay, did not miss anything here. Okay, it seems that I missed out some factor of 1 over 2. Okay, I missed 1 over 2 in both cases. Sorry. So we have 1 over 2 here at the above, and for below we have we can just substitute z equals to, again, d over 2. So it is same as the vector potential above. So for the upper plate, the vector potential across the surface, we can obtain the first boundary condition. The vector potential across the surface is continuous. And for the lower plate, again, we substitute for vector potential above, we substitute z equals to minus d over 2. So we get 1/2 of mu naught sigma v y hat. And for the vector potential below, it is okay, I missed the d here. It's the same. Okay, so again, we prove the first boundary condition, or we have shown the first boundary condition at the lower planes. Okay, for the second boundary condition, we have to take the derivative of the vector potential. Okay, so let me copy the result here. Okay, when we take the derivative for the upper region, the derivative of the vector potential with respect to z is clearly 0 because it is a constant. And same for the lower region. Okay, And for the middle region, taking the derivative is easy because, well, it just depends on that. So after taking the derivative, we just have mu naught sigma v left. Okay, so let's go back to the boundary condition and take a look at the second boundary condition. So for the upper plate, the derivative of the feather potential above A above is 0, and for A below it is this term, because for the upper plane, the above region is set greater than d over 2, and the below region is just the region in the middle of two planes. So we now have the difference being minus mu naught sigma v. And since sigma vy is the surface current density for the upper plane, so we can just write it as K1. So this is the second boundary condition. For the lower plate, okay, the region above the lower plate is the region between the two planes. So the derivative is this term, and for the lower region below, the derivative is just 0. So again, we have the difference being this time the sign is positive. However, for the lower plate, since the surface charge density is negative sigma, so the surface current density is negative sigma v y hat. So if we extract another minus side, we can get the same boundary condition, the second boundary condition, which is still minus mu naught times the surface current density. Okay, so that is the result of these two questions. So if you have any questions, feel free to email me or other TAs, or just post it on the discuss boards of the Blackboard. And that's all for today's exercise class. Thank you very much for coming. Goodbye.